Kia ora koutou, Marina, ko Yvette Wharton ahau. Good morning and welcome everyone. My name is Yvette Wharton and I'm chairing this workflow session today. We will have 3 presentations followed by a 10-minute break and then an additional presentation and a lightning talk. So we'll end promptly at 12:10, so we'll be sticking to the schedule as closely as possible. Any questions that you have for the presenters, please post them in the live Q&A, which can be accessed by clicking on the Q&A bottom on the bottom of your screen. If you have any technical difficulties, please select the red live support button in the top right corner of your screen. And if you leave, remember you can do this by clicking return to the timeline button on the top. So I'd like to invite our first speaker for today to the stage, Rose Pearson. She's a postdoctoral fellow at NZRSE and a visiting researcher at the Geospatial Research Institute. She'll be talking and discussing using public geospatial data in river flood modelling, and her talk is titled Flood Resilience Aotearoa, Engaging Aotearoa's Wealth of Public Geospatial Data.
Tēnā koutou katoa. So thanks for the introduction. I will be discussing research related to increasing Aotearoa's flood resilience by making use of our wealth of publicly available geoscience data. This is part of a much greater research program, which is Endeavour funded, which lasts 5 years in duration, and we're only 9 months into this research project. Today I'll be focusing on some open source software we've been developing for creating hydrologically conditioned digital elevation models and geofabric derivatives during the first 2 years of this research program. I wanted to start with a few visual examples from a selection of flood events over the last 7 years to illustrate the damage caused by flooding in our communities. Flooding is one of the world's most frequent and destructive natural hazards, causing $40 billion in damage worldwide every year. Here in New Zealand, in the 5 years to 2020, we had over 16 flood disasters, causing more than $200 million of insurance claim damage. Around 700,000 people, or more than a tenth of our population, and 400,000 buildings are presently directly exposed to river flooding during extreme weather events. The average annualized losses for flooding in New Zealand are estimated at over $500 million. And all of this is going to get worse with climate change. A key part of increasing New Zealand's flood resilience is being able to forecast river flooding across New Zealand in response to different storm events. The long-term and national focus of this program means that the process needs to be reproducible and updatable in response to new data, with a real focus on automation. If we think of the process of generating flood maps, we start with raw data. In this case, these are things like LiDAR, bathymetry, and infrastructure and river network databases. We take these at the catchment level and produce hydrologically conditioned digital elevation models and roughness maps, as well as extracting the relevant infrastructure and river information. These together can be considered geofabrics and combined with design storms. Design storms are the rainfall that we can expect in response to a storm. These storms can be historic, they can be what we might expect in a given year, or they can be they can look to the future and model the expected rainfall in response to climate change. We can expect increased intensity of these events. Together, these are combined and act as inputs to catchment level flood modelling. Here we're trying to produce 10 metre resolution flood models using a variety of tools, BGFlood, TopNet, and these produce the extent and depth of flood events in response to one of these design storms. The aim is to run many different storm events to be able to produce many different flood inundation maps, which can be combined both over all of New Zealand, but also for many different storm events, so we can get a sense of the hazard associated with each area, and of course the people, the risk to different population centres. For the rest of this talk, we'll be focusing on the generation of geofabrics as one stage in this overall process. Hydrologically conditioned DEMs are created from two major sources of data. LiDAR, which provides dense information on land. LiDARs, they produce many points. So a LiDAR survey is generally at the scale created from sort of aerial flights. And for one survey, you can expect many points in 1 metre. And these points are basically give the elevation of the land, surface of buildings, tops of trees, as well as inside the canopy of trees and the ground. Kind of quick rule of thumb is if you're standing on the ground and you can look up and see sunlight, some of the LiDAR points will be reflected off that surface. And these can be combined with bathymetry or water depth information, both in the ocean and also in rivers. There's a variety of ways in which these measurements can be attained, but in both cases, or in all cases, they're generally fairly sparse measurements. So we can have contour information or individual depth point measurements, but these are usually more in the order of every sort of kind of hundreds of meters or even kilometers, so a much sparser data set than LiDAR points. And we use coastline information to determine when we want to, when one data set is available or the other. Given the density of LiDAR points, we can use a much sort of denser, a different interpolation approach that's more appropriate for dense data. And when we have bathymetry information, we'll want to use an interpolation approach more appropriate for sparse data. The combination of these, we're combining this data to produce a dense grid of elevation information, where each point in that grid is giving the average height in that grid. So in this research project, we're aiming to produce 10 metre digital elevation models. So each point is a 10 by 10 metre square. And as we're concerned primarily with river flooding, we'd like that point to sort of indicate the elevation as water sees it. So representing the topography that water would flow over, or which means everything that water could flow through should be removed. These are things, land cover elements like bridges, forests, or buildings. And we really want to ensure that the river channels are preserved. Just wanted to use this, a visual example to illustrate the difference between a hydrologically and non-hydrologically conditioned digital elevation model. So to the left here, we can see a hydrologically conditioned DEM with all buildings removed. This shows the river mouth of Westport. You can see the river channel in the center of the image, and to the right of the image, as you can see in the non-hydrologically conditioned DEM, is Westport Township. To the left, all the buildings are removed. To the right, the buildings are retained. And you can also see stands of trees. You can see a bridge, which effectively is blocking the river channel. So those are elements that really need to be removed if the downstream flow modelling is to be accurate. Now, there are many other sources of information that need to be included and can be included to ensure the hydrological conditioning is better than it could be, and also included in the downstream flood modelling. Here, I wanted to sort of give a flavour of some of these other sources of information. We have things like river networks, which show the connectivity of river channels. To the right, we have infrastructure information. These are things like flood defences. You can consider stop banks, which are designed to impede the flow of water, and they might be of a spatial resolution less than 10 metres, so they need to be included in some other way in the flood modelling process. And in the centre, we have the classification of LiDAR points, which can be used to produce roughness maps, which a roughness map represents the drag water experiences when it's flowing over a DEM. So this incorporates the land cover information and is used with a hydrologically conditioned DEM to produce for flood modelling. I wanted to run through a quick example of the Westport area where we generated a DEM in response to the flooding experienced there in July of this year. We use publicly available geospatial data, which has been made available by LINS. We have in the top right, there's the sort of New Zealand layer or polygon representing the coast, the islands of New Zealand, and then below that we also have depth contours or bathymetry information offshore of New Zealand. And we were able to use these in combination for the recently acquired LiDAR survey over Westport, which was acquired early to mid 2020. And together we use these to produce a DEM. So those are publicly available data sets, which can be accessed through online web portals, allowing for the data to be queried spatially or by name. And to the left here, we have a catchment that was quickly delineated by one of our modelers, and this is where we wanted to produce our DEM. We've been developing GeoFabrics, which is an open source software package which is available on GitHub with instructions for installation and usage on its wiki, which we've been using to produce these DEMs. And here we've had a real focus on repeatability and automation. We've been using GitHub Actions to test it, to run our tests in Linux and Windows to ensure no unplanned changes. And we've been using a robust PR process with all changes reviewed. And we've kind of here ensured we add new tests for new functionality, just so we can make sure that the repeatability, be confident in the repeatability of our package. Really quickly, I just wanted to illustrate how this package can be used. It's basically Python code controlled for using a JSON instruction file. And the key components of this instruction file are some output information about the DEM we want to produce, namely its resolution. And then secondarily, we also have the source data location, basically the online data surfaces we'd like to query the information from, and then where we want to produce our outputs. So just wanted to quickly look at the results for our DEM in Westport. You can see to the right, we have Westport Township, and if we look at the results there, generally the buildings and the like have been removed. However, we can see clear artifact due to poor reflections off the river and no river bathymetry currently being incorporated. So it's a real focus for us in the future. I also wanted to quickly touch on GeoAPIs, which is a package we've split out from GeoFabrics, as we think it's generally useful functionality to manage the downloading of publicly available geoscience data, geospatial data, with easy-to-use interface to enable more researchers to access these datasets at scale. Supports the bulk download of LiDAR point clouds within a polygon with no need to muck around with AWS S3 protocol, and also the bulk download of GIS data from the LINS data service and a variety of other data services like Stats New Zealand again, without having to muck around with URL wrangling. In the future, we intend to support raster data and will continue to add other sources of online GIS data. What's next? Well, we've still got a year and a quarter of our time, and we are focusing on increasing the processing efficiency, making use of parallel processing on NZRSE, generating roughness maps. We'd like to publish geo APIs on PyPy to facilitate others to sort of lower the barrier to entry. And in future, we need to incorporate river bathymetry and other river network information, improve the LiDAR classification, and then make sure that this piece of the processing chain is integrated with HERD's TopNet and BG-Flood, the design storm and flood modeling tools. And finally, we would like to ensure, or we are working with LINS to ensure that the geofabric derivatives, as well as eventually the flood maps, can be published to LINS data services so they can be used by councils or other consultancies in their work to help increase New Zealand's flood resilience. Thank you. I guess any questions?
We have one question from Alexander saying, thank you, Rose. Do you use parallelism in your workflows, e.g. job arrays or some other mechanisms?
Hi, Alexander. Currently, I've not. I've focused on, I guess, getting the sort of full pipeline created as quickly as possible, but I'm now looking into that. So I've been looking at Dask, possibly using something like a more kind of hands-on approach, like microprocessing. So this has been developed so far in Python, and I think given the processing load, we'll be able to stay there. So yeah, we're looking at Dask and number, and if that doesn't work, looking at microprocessing. But there are a few stages in the processing chain where we're dealing with tiled information, or we're producing our we're doing our interpolation in a tiled approach. So there's a lot of scope there to parallelize those portions of the workflow.
While we're waiting for other people to ask questions, I have one from me. What were the biggest challenges for you in developing this workflow and making sure it was sort of open and reproducible?
Well, I would say first, we're not by any means finished, so these challenges continue. I think firstly, it was probably making use of the tools that are available, making sure the software is designed and our development process is designed to kind of make use of that. So using GitHub Actions, for instance, was definitely a big step forward, as that way we don't need to manually run the tests on our local machines, but also for free we have testing on Windows where I'm developing, but also Linux, as there are a few areas where at various times we're getting quite different results between those two operating systems, which is a clear indication of, well, lack of reproducibility, if nothing else. And I guess getting in the habit of adding tests as we added new functionality really aided with that as well. And then I guess the final comment would be sort of I spent a little bit of time at the beginning looking at different Python packages that were available, and that really sped up the development, so we could focus on combining these rich tool sets, I guess, instead of doing some of the lower level development, like dealing with, say, reading in LiDAR files or tiling LiDAR files or the like. Being able to use some of these high level packages really sped that up. Things like PDAL or GDAL or raster.io or RIO.
Okay, so there are two more questions, so we'll see how quickly we can get through those. The first is, does your modelling include the impacts of sea level rise due to climate change?
So not, I guess, my portion, which is producing the DEM, as I guess the only impact there would be erosion over time, and that can be incorporated by doing different LiDAR. or incorporating different LiDAR information. The overall project, there is a, I guess, secondary focus. As it's focused on river flooding, the greater impact there is the change in the intensity of storms as opposed to the increase of sea level. But there is early work investigating or including changes in sea level in those modelling, I guess, runs in the flood modelling.
And one final question before we move on. How easily is it movable across other compute infrastructure? And do you have any opportunities to get a naive user to try to run this from scratch on another HPC?
At this stage, as we're just moving to the HPC environment, I'd say it's pretty, it would be easily used across any HPC environment. It just won't be very fast. And as we're looking at using things like, or focusing on kind of high level processing tools, as long as it, as long as Python and a basic Python sort of scientific stack supported it, you will be able to use it on different HPC environments. As for the use by sort of naive users, a part of the Greater Endeavour project, as part of that, there are some PhD students that are funded, and this tool will be part of their greater research project. So perhaps not a naive user, but certainly there'll be other people using this tool. Thanks.
Thank you. So our next speaker is Alena Malyarenko, a postdoctoral fellow within the Antarctic Science Platform, and her talk's titled Coupled Climate Ice Ocean Modelling, Setting Up a Framework.
Why can't I? Yes. So I'm going to be talking about the climate ice ocean modeling, and this is the work that I've been doing with Alex Gossard, who is another postdoc within the Antarctic Science Platform. So I'm going to just quickly run through what is a coupled model, how we're setting up models to work, how we're trying to balance exchange through the model interfaces, and what are the future projections for climate change and our future plans in this area. So when we talk about a climate ice ocean model, we talk about several different objects. First of all, there's an Antarctic ice sheet, and we are focusing currently in the Ross Sea, which is just south from New Zealand. As the Antarctic ice sheet slides off the continent, it is floating on top of the ocean, and at which point it's called the ice shelf. At the ice shelf front, the ice shelf itself can still be up to 300-400 meters thick, and then the ocean underneath it can be another 800 meters thick. So this is where the ocean cavity modeling comes in. The ice shelf can melt, break apart, create the small icebergs, and this is where the ocean ice shelf interaction comes in. But if we look at a typical winter satellite observation, in the Ross Sea, there are three major polynyas. Polynyas are areas of open water in winter where the wind keeps blowing sea ice away from the coastline and keeps breaking the sea ice and just making new sea ice. These three polynyas, they look small, but they actually are responsible for up to 25% of the bottom water formation in the whole ocean. So they're very important atmosphere-sea ice interactions here. So we have four major components: atmosphere, ice sheet, sea ice, and ocean, and any of them can be in contact with each other. So we are using the WRF, the Weather Research and Forecast model for the atmosphere. And then we are very lucky because the model that I'm using, MIT GCM, actually can represent the three other objects: an ice sheet, sea ice, and ocean. And all of them have ability to move, melt, interact with other ones. And so we've added the ESMF, so Earth System Modeling Framework, to connect those two big models. And it comes with an interoperability layer in between those. And now those three models together become the Scripps-Kaust model that we've been using. So when we're setting up these models to work, First of all, we just had to figure out the folder structures. The two models are incredibly complex and convoluted, and just getting them all together in one spot was a feat on itself, and trying to figure out what's needed for compilation and what's needed for runs. We also had a funny task of domain coordination. As we both set the domains, as you can see on this plot, they did not match, even though we were using the same bathymetry data sets, because the models do a little bit of a black box interpolation. We couldn't really control it well. But if some of these errors can be said, oh, well, this was the iceberg that detached, and you can explain them. I mean, we had problems with island positions, and they clearly do not move that much. So we had to go and hack that part too, so that our coupling actually matched. And then we had to figure out how these three models would work together. And so it seems that WRF and MIT-GCM are compiled as libraries and then included in the coupler that then just calls them as functions. And so once we moved to Mai, we had another problem. Both me and Alex had NZRSE consultancies, which recommended two different compilers for our models. And it turns out that our models do not really like each other's compilers. So with the Cray and Peach, which was recommended for MIT-GCM, WRF just did not want to compile. And with Intel, ESMF had to be reinstalled, and MIT-GCM had to go through a couple of corrections in the code itself to make it compile and run. And I mean, honestly, it all sounds incredibly simple, but it took us 2 months to even start the models running. So I'm incredibly proud of this bit. The models can run in sequential or concurrent coupling mode. So sequential mode means that one model runs after another and then they exchange information, and concurrent means that both of them run together. The ocean model is an order of magnitude smaller than the atmosphere model. In our setup, I can run the ocean model on one node, and then the atmosphere model requires about 15 nodes. So in concurrent mode, which we are choosing, we can assign different number of CPUs to both models. And yes, the ocean model will still have to wait until the atmosphere model finished the time step, but at least we're not going to wait on 15 nodes. This is a little bit more sciencey bit of this work, is that we're trying to balance the exchange for the interface. So in general, the atmosphere and the ocean there are 3 situations how these models kind of interact. One, this is just the atmosphere over the open ocean, the second one over sea ice, and the third over the ice shelf. So when we are working just in the atmosphere ocean situation, ocean sends up sea surface temperature and ocean currents, and then the atmosphere sends down solar and turbulent fluxes, wind, and rain or snow precipitation. If you add sea ice as a layer in the middle, we actually had to split sea ice and snow on sea ice between 2 different models. So now sea ice is moved within MIT-GCM. It can advect, it can move, grow, and do things like that. And then we give ice and snow area to the WRF model, which has a very sophisticated snowpack model, even for snow on sea ice. So now WRF model spends the fluxes that it takes to grow or melt snowpack, and then the residual fluxes and the updated snow variable are given to the sea ice component of MIT-GCM instead of kind of the main fluxes that you would give in the first place. And we also had to catch snow on sea ice melting. This is a variable that WRF can just disappears into the ether because, well, the ocean can deal with it. But now in the coupled modeling, we had to assign this variable and put it into the ocean because this is the extra fresh water that we have to account for. And a similar situation is with the ice sheet modeling. So the snow on the ice shelf or on the ice sheet is now computed within the atmosphere model. Surface melt variable that actually changes the shape of the ice sheet is transmitted to the ice sheet portion of MIT-GCM. And snow melt, which again was just disappearing as warp, is now collected and then put in the open ocean right next to the ice shelf front here. From the ocean side, now temperature and currents actually melt the ice sheet, and it can evolve in its shelf and its shape, and the ice sheet can give the meltwater so this is the mass flux and the heat flux back into the ocean. So this is a bit of a complex interplay between all of these variables. This is our current work on future projections. We're doing only the Ross Sea and with 10-kilometer resolution. So here on the ocean side, we're doing boundary condition pre-processing, and the ocean domain actually needs a pretty long spin up, about 10 years, because none of the initial condition data includes the ocean cavities, so that ocean under the ice shelves. We have to spin it up ourselves. On the atmosphere side, there's again some pre-processing, but the spin up is about 5 days long, just because the atmosphere changes so quickly. And this can be done in just 7 hours on those 15 nodes. So once those two things are ready, we can move into a 5-year coupled run with, again, boundary conditions for these 5-year run. So in our estimate, the ocean can just continue working on this one node for about 200 hours. The atmosphere will need about 10 times more. The coupler itself is actually a single CPU task, and we are not clear how long it will take us to do the wait time so far. So we've calculated that for everything but the atmosphere run, we will need 800 node hours and then 36,000 node hours for the atmosphere 5-year run. So clearly that's a bottleneck, very well defined. And for future work, I mean, the first bit of it is actually the Ross Sea ocean models need to have a much higher resolution. We're currently running at 10 kilometers, and we need to move to about 2 kilometers. And here I'm showing the example of how the McMurdo Sound looks with 10 and 2 kilometer resolution. I had to remove both islands and some peninsulas just to make the model a little bit more stable, but it actually changed the ocean circulation significantly. Now there is this huge outflow from under the Ross ice shelf, which doesn't really exist in reality. Of course, if we move the ocean to that high resolution, the atmosphere can't move with it because it's just going to be even more heavier. So we're going to have to introduce the regridding and reinterpolation in that coupler. So that's going to take a little bit longer. And the atmosphere model needs to be as light as possible. We think that winds are actually the most important parameter in this coupling setup to not lose. So we want the winds to be strong enough to keep blowing the sea ice away and to make the polynyas. And now the question for Alex is how much complexity and resolution in the atmosphere model we can sacrifice and still get those winds and polynyas working. We don't currently have an ice sheet component, and we're going to turn it on when we have time to work. And of course, the Antarctic Science Platform would like to have Antarctic-wide projections. And I can only imagine just how much more node hours we would need for that. And that's about it for me.
Ngā mihi nui, Alena. That was a really interesting talk, and particularly in one of our remote and pristine environments. So Jean has a question for you. Alena, this coupled model also applicable to Antarctica and to the Antarctic region? Sorry, the Arctic region, or Northern Hemisphere? Does it have a different modeling technique?
I mean, it's actually going to be even simpler there because we wouldn't have to worry about the ice sheet for the Arctic Ocean. We would have to turn it on for Greenland, obviously. But yes, this is just a matter of setting up domains and coordinating them. But once the framework works, you can apply it to any other region.
And then a question from Emily Lane. Kia ora, Alena. Thanks for your interesting talk. Do you consider the effect of waves in this modelling? If not, how much more effort would be required for this?
So No, we don't have a wave model coupled to this. And honestly, I don't ever want to try to do that because that would just increase the complexity. We've just turned on tides in the ocean model, and that already increased the computational time significantly. I know waves are very important in the marginal ice zone, but because the Ross Sea itself is mostly covered by sea ice, I'm kind of happy to let it go for a while.
And from Alexander, thanks, Alena. Do you expect the sequential coupling to give more accurate results? The second component gets more up-to-date fluxes than when using concurrent coupling.
I think the exchange of the data itself is the same. It's just a question of when exactly it happens and who is waiting for how long out of those two components. But as we can obviously change the time, right now the recommended exchange for coupling is about 60 seconds. We obviously will not go to do this. We're going to do it at least an hour because otherwise it's going to take just too long. Yeah, but I think it doesn't matter for the exchange of variables, the type we couple, but I may be wrong.
And a follow-up question from Jean. Does the model take into account Antarctic ground effect?
I don't know what Antarctic ground effect is.
Maybe you can have a separate conversation with Jean.
So in the ice sheet model itself moves so that if it does melt, there's going to be a grounding line change position. So the ice shelf can move away and retreat and make even worse sea level rise projections. Yeah, but this is obviously years ahead of us in terms of when we'll get to turning all of the bits on.
Okay, so that looks like all the questions people have asked so far. Thank you, Alena, and we'll introduce our next speaker, who is Richard Lupat, and he's going to be discussing workflow interoperability with the talk titled Janis, sorry, a Python framework for workflow translation.
Hey, good morning, everyone, and thanks for the introduction. So my name is Richard. So I'm a biomedical software engineer at Peter MacCallum Cancer Centre in Melbourne, Australia. Today, I'll be talking about Janis, which is a Python framework for workflow translation. It's part of a portable pipelines project, which is a collaboration between multiple institutes, namely Peter MacCallum Cancer Centre, where I'm based, Melbourne Biomedics at the University of Melbourne, Walter and Eliza Hall Institute of Medical Research, and Australian Biocommons. And the motivations of this project is namely, we would like to share workflows, and we would like these workflows to be portable, and eventually we'll be able to publish this analysis. We also do not want to reinvent the wheels. We want to adhere to any standards in the workflow community, and we want our solutions to be reusable. So the main considerations that we put into thought when we kind of designed the solution was because we're coming mostly from the bioinformatics sort of community, the workflows and the pipelines in this kind of domain mostly try to link multiple tools in a complex sort of bioinformatics workflows. And these multiple tools comes from different institutes, developed by different institutes across the globes. They're mostly very heavy in input-outputs, so very text-based. And they all come in all sorts of languages like Python, Java, Scala, Groovy, and all that. And how are we going to go and share this? And the recent adoptions of containers such as Docker and Singularity has greatly helped us package all these different dependencies, libraries, and make this research more reproducible and give us the opportunity to be able to publish this sort of analysis of our data. But on the other hand, our data sets get bigger and bigger. The scale of new data sets coming in and the type of data get even massive. But fortunately, all these analyses are also embarrassingly parallel. And at the end, one important part that we kind of want to consider is how do we decouple our analysis from the underlying infrastructure, such as we want to be able for researchers to run this on their local laptop, as well as running it on our institute's high-performance computing system, and also on the commercial clouds or research clouds environments. So I mentioned a lot about portability, but why is portability important? So the first part is, well, data is very hard to move around. So it involves a long transfer times, and most of the time it's very costly. And computing availability on-prem is also limited. So with the cloud, you get the flexibility to do a burst computing. And then there is also a combination of cost optimization where you can do some hybrid, some preemptible or spot instances to save some cost on computations when needed. And I guess this is where the trend is mostly going to, is we want to be able to bring the pipeline of your workflow to the data instead of bringing the data to your computation system. So this is particularly important as the number of public data sets keep growing, such as the likes of the Cancer Genome Atlas, some reference genomes that's available widely in different cloud buckets, and we would like to be able to directly launch our analysis up there instead of bringing data back on-prem. None of these the problems are really new. There are lots of workflow systems have already been developed. You probably have seen one of them from the workshop yesterday, SnakeMake. So it's normally a combination of specification and a workflow engine. So people have been trying to abstract the specification away from the batch system. For example, you will be able to run this in SLAM, PBS to better utilize the resources. Is decoupled from the underlying file system, whether it's a shared file system like GPFS, NFS, Google Bucket, S3, that sort of help us move the pipelines much easier, especially as people try to move towards cloud computing. And the advantages of using this kind of workflow manager is it keeps the pipeline development away from having to think about those restart, how to restart a fail analysis, how to continue, rerun, input, output, checking, logging, notifications, which will all be handled by the workflow manager. And there are lots of workflow manager, and these are some of the existing specifications that people are trying to better abstract the specification away from the workflow manager. So for example, the common workflow language, CWL, which is a sort of YAML specification key value pairs that has a multitude of engines and tools supporting it. There's a large community behind it. And there's also workflow definition language, WIDL, which is developed by Broad Institute. And it's a custom DSL. It's mostly used for sort of genomics and bioinformatics type of workflows. There's also Nextflow and SnakeMake, BPython, and other type of existing specifications. And if we kind of bring this into a diagram, so if you see on the left, we got the specification. You got CWL, WIDL, Nextflow, and this all has these individual engines, CWL tool, Toil, Cromwell that can execute the specification. And then the combination of all this specification will be able to capture all kind of compute environments. So, for example, one specification might be better you run on certain type of HPCs or integrate better with natively with AWS or Google Cloud, one or the other. But you wouldn't be naturally find one that might be able to capture everything. There might be one eventually one day, but as far as we've tested currently, one will normally work better than the other, and vice versa. So, and then it comes to that discussion when a researcher asks us, so if I would like to build a new pipeline today, so do I start with CWL, do I start with WIDL, or do I start with Nextflow? Each of them comes with their benefits, comes with their communities, comes with their own tools and tasks and pipelines behind it. And our solution was a bit more high level. So instead of doing that one by one, we would like to generate CWL without a Nextflow. We don't want to necessarily re-implement what they've done, but we want to isolate us, prevent us from having to rewrite in the future. So we write one, and having that support to translate our workflow specifications into some of these languages in the future, or adding a support of new languages in the future. So this gives us the flexibility of which workflow specification to go, the choice of execution engines, and we kind of reward it with the best of all these multiple technologies. And that brings us to this project that we've been working on called Janis. So it's a Python framework. It has simple APIs, it builds workflow wrap tools, it has some type safety connections. It can generate CWL, Widow, Nextflow, and we're currently working towards Galaxy as well. It has a toolbox of tools and types. So if you take an example of a hello world in this side, so it's a Python sort of script that imports echo Janis unit tool. So it's a pretty simple tools, taking one input of a string, and then it will print that string out back to standard out. And if you run a Janis translate that Janis Python tools to CWL, Widow, and Nextflow, you'll get the CWL equivalent of the workflow on the left side, the Widow equivalent of that workflow in the middle, and the Nextflow equivalent on the right. So this gives you the flexibility to run any of these workflows in any of the execution engines of your choice in their native sort of environment that supports this workflow. So if we dive deeper into the syntax, so a Janis command tool, if you wrap it, it consists of the declaration at the top where you import some of the Janis functions and Janis data types. You create the object. In this case, we take BWA mem tools as an example. This is a tool for aligning a next generation sequencing data to the reference genome. You create an ID of the tool, add the command of how to run the tool, add the inputs for these tools, what's the output, and then the version of the tool. In this case, we're mostly going to be dealing with containers, especially tools that are being published into Bioconda or biocontainers, and then add the necessary version for reproducibility. So this sort of format mostly follows the convention that CWL and Widow has, except this is in a Python class object format. For the workflow side, it's very similar to the command line tool specification. So you import some of the Janis functions, you declare the objects of their workflows, you create the input of the workflows, and what's the step involved in that workflow. In this case, we only have a single step called BWMM that we declared earlier. And then you create an output that captures a workflow output coming from the step output. So if we go back to our diagram of the multiple specifications, now we have a single Janis specifications that will be able to target multiple specifications, which will then be able to target multiple execution engines and eventually also the outputs. Also the compute environments that gives you all the outputs. And all that is cool, but you wouldn't want to, not everyone would like to just keep translating and then run it separately. So on top of that, we have an extra wrappers to help running the workflows, to progress, monitor the workflows that's running, to standardize the output collections from different engine modifications. So in that way, you can do Janis run a particular workflow. So just to be clear, none of these are an actual engine. What it's doing is actually managing a different workflow engine that runs the actual analysis. And you'll be able to run the likes of Janis Watch to monitor how your analysis is going, how many steps are still going, and how long it takes for a particular tool to run. So, and then if we sort of the architecture of how this Janis assistant is doing is, so we've seen the Janis specification at the top that translate to different specifications, CWL, Widow, and other specification, and Janis assistant job is to take that specification, launch the engines, and monitor them. That's good if you want to create a workflow from scratch. So what if you already have existing workflows, and what do we do in order to migrate existing workflows? after all, that's the hard part of the sort of the workflow, what workflow community is trying to do in order to get that interoperability. So what Janis is also trying to do is to be able to convert any valid CWL widow workflows into Janis, and that allows these workflows to be further translated into all the other Janis supported translations. So in the example that I put here there is this function that we implemented called from CWL that will be able to pass any existing CWL into Janis, and then you'll be able to output the widow equivalent of these particular workflows. And we've tested this on a kids-first pipelines that that do analysis on genomics for pediatric genome. Some of the challenges of trying to tackle this interoperability is interpreting custom DSL is not particularly straightforward, especially some of these workflow system supports adding of a custom function. So it's like you can implement these functions, JavaScript and Groovy, and eventually we need to have a parser that will be able to understand a full programming language, which in itself is a pretty tough challenge. And this results in a very complex translated workflow. So we'll be able to wrap all these little functions into its tool itself, but at the results, the translated workflows become very hardly to read. And trying to guess types of a particular file's inputs is pretty challenging for coming from a workflow that doesn't support typing. And at the end, this means that we still need human to try to fix the translation between different workflows. And for the time being, we can only support up until 80% of the full translation, namely struggle to deal with all these custom functions. There are other features in Janis that didn't have the time to cover today. Things like the typing system. It supports conditionals, just like any other workflow system. You can do custom Python functions that will launch a Python container that runs a single or multiple Python tools. You can do scatter-gather, so that's kind of splitting your files into smaller chunks, running in parallel, and then gather them back together. You can create your own private toolboxes if you don't want to use any of our existing toolboxes. Some of the future work of Janis is we try to build the community. We're currently working mostly on cancer genomics domain, and we would like to expand the use of Janis to cover use cases beyond just cancer genomics. And we would like to support more users and eventually build the community to be bigger. And in terms of the actual technical work, we are currently working, putting further work towards the workflow interoperability. So in a sense that we try to improve the from CWL and from widow functions, and also currently adding Galaxy passes into the toolbox. And in summary, Janis is a Python module for building workflows. It gives you a CWL widow next flow from your Python functions. It also has an assistant to help you run workflows after the translations. And it's also support for passing existing workflows into Janis. All the codes are in GitHub. We have all the documentations in Janis Read the Docs page. There is a guitar. If anyone would like to give it a try and have any questions, please reach out at guitar. The instruction on how to install it is all installable through pip. And that's it for me, and put out slides to acknowledge all the people that's involved in this project and all our collaborators across multiple institutes. And thank you.
Ngā mihi nui, Richard. We have a couple of questions from Roland Mosbergen. Hi, Richard. Do you see Janis uptake being from people using cloud compute or from on-premise compute as the majority?
Thanks for the question. I think currently most of our users are HPC users rather than cloud users, although we've seen our motivation initially, I think, is to target all type of different environments, whether it's cloud or HPC. I think the adoptions of cloud in this kind of environment is not as fast as we hope it will be yet, namely because of the costs involved in doing genomics cloud computing. So if it was up to me, my prediction would be it will eventually pick up in terms of cloud adoptions, but currently it's majority HPC.
And then a follow-up on that, do you see Whittle being more stable, but CWL introducing more changes due to their relative maturities? And does that pose challenges for you to keep up to date?
Yes, so that's a great question. And I think that is definitely hit the point. The challenges is how do we keep up with the changes coming from different workflow specifications? We need to keep updating our translations in order to match that, or we stick to a particular version of each of the specifications. But that, and referring back to the first statements, we actually don't see much of the breaking changes from either Whittle and CWL currently, and whether the adoptions of which one comes bigger in the future, it's still pretty questionable. Nextflow itself is actually getting bigger than the other two. And obviously on the side, you got people still, a lot of current workflows that actually runs NetMake, and a lot of biomedical scientists actually using Galaxy for their analysis. So there is no one solution that fits all. And we hope Janis will be able to bridge that to kind of bring the communities together through translating the workflows between these specifications.
And then last question from Roland. When you are about to start on Janis, say to migrate an existing workflow, is there a way to know beforehand if it will be covered by the 80% or not?
Yes, so when you start that migration, essentially, you just put in your whole workflows into that our development toolkit, and then it will give you all the translation. And as part of that translation, it will tell you which part of that 20% that it couldn't cover. So it will tell you, for example, your workflows has about like 20 or 50 different tasks, and then it will give you like that 10, I couldn't do much about this, you need to fix this part yourself, and then give you some warning and critical error and pointers to how you can do it and where to look for.
So do we have any other questions for Richard? If not, I'm going to say thank you to all our speakers that we've had so far. We are going to take an eco break for 10 minutes. Get up and stretch your legs, give your eyes a rest, and we'll be back here for 11:40 for our next speaker in our Workflows Session B.